All right, we're going to look at lesson 5.2, and it's about polynomial functions. We've already started looking at it. You've investigated some properties. You've investigated looking at the graphs. You've compared and contrast graphs. Those two investigations were both done in Desmos, and this is the follow-up. Okay, so we're going to be identifying zeros, looking at multiplicities. We saw that in Desmos. End behavior, that was the second Desmos. Mins and maxes we found on the calculator the other day. And then we're also going to write polynomials given certain criteria. So this is kind of summarizing what we've seen in the past two Desmos and putting this all together into how do we graph a polynomial function and how do I write an equation of a polynomial function from either the graph or from certain characteristics. So one of the things we know is that if x minus a is a linear factor of a polynomial, that if and only if a is a zero of that polynomial. So if I know x plus 5, x plus 3, and x minus 4 are the factors of a cubic, then I'm going to cross at these three spots. But the question of how am I going to cross at those spots is going to vary based on other things, especially based on if there's a positive or negative here, and if there's any squares on any of this, and or cubes or powers on any of these. So if there's a power here or a power here or a power here, that's going to affect how this graph looks. So if I know these are the factors, I know I'm going to cross at those points, but these other purple boxes or circles are going to impact what the graph looks like. So if I wanted a cubic polynomial, so that tells me I'm going to be at degree 3, with zeros at x equal at 5, negative 2, and 4, I would take that and say x minus 5, x plus 2, I'm going to use that stray mark as a plus sign, and x minus 4. That is one example that has zeros at those 3 points. But wait, there's probably other polynomials that will also have that. You would also have y equals 2 times x minus 5 times x plus 2 times x minus 4. That would be another polynomial. It would have a vertical stretch of 2 on it. And I could even have, let me change the color. Oh, no, I don't want that. I could even have negative x minus 5, x plus 2, x minus 4 as another polynomial. This would have a reflection. Now, this particular problem didn't say anything about a y-intercept or another point on the graph or any other information about that would give us an indication of the end behavior on this graph. So I don't know if it should be reflected or not. I don't know if it should have any of these other ones. So in those cases, I generally just write an A in front of that. And that A is to represent that it could be a multiple of any one of these, okay, because it's generic enough with my description. So write a cubic polynomial with zeros at negative 2, and 1 that goes through the point 0, 8. Now see this extra piece of information? This is going to have only one correct answer. And that's because I'm giving another piece of information in the problem. So I'm going to have y equals x plus 2 multiplied by an x plus 2. So notice I have this written there twice. That's why I have 2 of those. And x minus 1. I'm also going to squeak that a in front for a moment, okay? But I will eventually find what that a value is. What I'm going to do to find that a value is I'm going to make the x a 0 and my y 8. And I will find what a is. So 8 is equal to 2 times negative 1. So negative 4a is equal to 8. So a must be negative 2. This must have a vertical stretch of 2 and is reflected over the x-axis. And while I write this, I'm going to write x plus 2 quantities squared. Ooh, so fancy. Okay, this is the only cubic polynomial with those I'm going to say 3 because it had 3 pieces, but actually really only 2 because one of them is duplicated or is a double root that goes through the point 0, 8 with those x-intercepts. So if you notice on the last problem that -2 is repeated, we call that repeated 0 either a multiple root or a multiplicity. We saw that in Desmos when you had to try and shimmy the graph so that it crossed once and then bounced on this other one. Okay, so that multiplicity came from this kind of bounce. And on this last one, this graph would look something like -2, +1, and 0, 8. So it would go down through there, and then you would see this bounce happen there roughly. So find the zeros of the function indicated in any multiplicities. So the zeros of the function, we're going to set y equal to 0, and then we're going to factor. And it's a good thing we're really good at factoring from the last unit, because things in math are all connected, because now we need those skills here. I know the x squared's there. So this one is a 0. Notice the exponent up in this spot right here. Up here, that exponent, that's the piece that's telling me an even multiplicity. So 0 with a multiplicity of 2, -4, and -2. Now, ooh, look at this. We've got 3. Can the number 2 ever equal 0? No, so that doesn't have one. -2 with a multiplicity of 2, because that's that exponent. And we also have 1 with a multiplicity of 3. I'm kind of happy that that one was factored for us. Now, a follow-up question. What does it look like graphically? Well, take a moment and either open up Desmos or take out your calculator, and let's take a look at this graph, x to the 4th plus 6x cubed plus 8x squared. You might have already a good idea of what's going to happen at that 0 with that multiples root, because again, this one had 0 multiplicity of 2 and -4 and -2. I'll jot those down. But let's take a look at it in one of our uses of technology. So, sorry. If I bring this over, we're going to graph x to the 4th plus, oops, sorry, I had to take a look at it. 3rd plus 8x squared. And fix my window. So the graph looks something like this. Oops, sorry. So you can see how we're crossing at -4. We cross at -2, but you have this spot here where it was in the positives and it didn't cross. It kind of bounced along that axis. We call that being tangent to the x-axis. So even multiplicities, so that's if it's the power squared or to the 4th or to the 6th or to the 8th, are going to be tangent to the graph. Okay, it's tangent to the x-axis. It's going to basically just touch it once or bounce on the axis, kind of like that. Okay, the higher the power, the more flat it will, just like our power functions. So if this would be like an x, I don't know, like -2 squared in the function, then if I had to the 4th, it would flatten a little bit more if I had x -2 to the 4th in it. Similar to our power functions. That's why we looked at power functions earlier. Odd multiplicities are going to go through the point. So if you have like x -3, it's going to go through kind of linearly. If I have x -3 to the 3rd as one of my powers, at this 3, it's going to kind of go through and flatten as it goes through. So one of the other big things that we saw in the Desmos after the unit test was classifying things by the end behavior, how the graph acts as x approaches infinity or negative infinity. So There are 4 ways to classify end behavior. You can classify them as up, and that means as x goes to infinity, the outputs are going to infinity, and as x goes to negative infinity, the outputs are going to positive infinity. You can classify as down, down. I can call that down, down like a frown. You can classify as down, up, or you can classify as up, down. Now, the things that you hopefully noticed from the Desmos is these up, and down, down both have even degrees. But what you see here is, this one has a positive leading coefficient, whereas this one has a negative leading coefficient. That's what creates it to go down instead of up. For my down, up, and up, down, hopefully you notice that these both have odd degree. And again, the down, up has a positive leading coefficient. And the up, down has a negative leading coefficient for that, from that reflection basically in the factored form. Okay. Another way to organize the same information would be to say even and odd, positive and negative. Even and positive is up, up. Even and negative is down, down. Positive and odd is down, up. Positive and negative is up, down. Most people don't struggle with the even end behaviors, it's the odd ones. So the way I remember it is this has a positive slope and this has a negative slope. And then if you just take your eraser and just boop, and there's your up, down. All right, so now, one other piece of notes. A polynomial of degree n can have as most n minus 1 turning points, and that's because the number of turning points has to be smaller than the degree. So let's take a look. Let's take a look at finding the zeros, the y-intercept, local min and local max. Those two you have to do with Desmos or the calculator. And then we're going to sketch a graph. So I'll probably sketch my graph and then I'll go back and confirm with Desmos and find that local min and local max there. So I'm going to first factor. So I can pull out a 4x squared, x minus 3. I can pull out a negative 1, x minus 3. See, this is a grouping one because I had 4 terms. 4x squared minus 1 multiplied by an x minus 3. And difference of squares. Oops, sorry. Okay, so x is 1/2, negative 1/2, and positive 3. Now, the other thing I want to do is what my end behavior is. So my end behavior on this one, I have an odd and positive. And so my odd is telling me opposite directions. My positive is telling me I'm starting down and ending up, or down, up, if you write it in words. So there are no multiplicities on any of my x-intercepts, so I don't have any bounces or things like that. And so I cross at 1, 2, 3, 1/2, negative 1/2. This part is going down. My y-intercept is positive 3. So I'm going to add that. Those are x-intercepts. So there's my x-intercepts, my end behavior, and my y-intercept, and that made my sketch. Now, it looks on my graph that this 0, 3 is a max, and somewhere around maybe positive 2 and then a negative value, or positive 1.5. We're not going to find those algebraically. That's about what my sketch is looking like. but I'm going to use either Desmos or my graphing calculator to find those. We practiced finding them with the graphing calculator the other day. All right, so we have our graph looking something like this. You can see my max, ooh, it wasn't exactly at 3. It was a smidge over to the side. Look at that. So here's my graph in Desmos, the accurate one. I would say my sketch is a pretty good model, though. Again, when we're doing these, we're not graphing them super precisely. We're just doing a sketch based on the x-intercepts, the y-intercept, if we have it, and the multiplicities and end behavior. So this is my local max, and this is my local min. We call them local ones because it's not over the entire function, but rather just in this section of the graph. And this, actually, we'll do one more problem. I have one more problem here. An open box is created from a square sheet of metal by cutting small squares from each corner. So here's our square piece of metal, and we're cutting little tiny squares out of the corners. Originally, the square measured 10 on each side. That was the original square. What size square should be cut off to maximize the volume of the box? Just as a reminder, we're not going to use negative b over 2a because this is going to be a polynomial and not necessarily quadratic. It's probably going to be cubic. So my squares here are x by x, because I don't know how big they are, so I'm going to call them x. Now, this length here, from here to here, that had been 10, and I've cut off x from each side, so it's going to be 10 minus 2x. This side will be 10 minus 2x. Now, when I fold this up, the base of my rectangular prism will be 10 minus 2x by another 10 minus 2x. And then here, I'm going to have a height of x all the way around. And that's from basically that this seam and this seam are going to match each other as it folds up. So when I find my volume, I'm going to say x times 10 minus 2x times another 10 minus 2x, but I'm just going to write 10 minus 2x squared. I am not going to multiply this out. I know. I'm actually going to use that it's going to cross at 0. And this one's going to be 5. It's going to bounce at 5. And my end behavior here, this would be a positive cubic. So this is going to go down, and then it's going to go up and bounce. So what we want to find is this local max right here. The question is going to be, what is that value? So since I can't find those values algebraically, this is where I'm going to take out my graphing calculator or Desmos to take a look at that. So go ahead and finish this problem off on your own. Did you get a local max? All right, so here's what we're going to get. The graph should look something like this. Okay. It takes a little while to get used to finding a good window, but I would do like -1 to 10 and 0 to 100 for right now. And so you can see there's my max. So the size of the square should be is 1.667. So I'm going to say 1 2/3. And the unit was inches. So x is 1 2/3 inches. Final answer. And this concludes lesson 5.2.